In this video, I'll be talking about the normal distribution. Unlike the binomial and Poisson distribution, the normal distribution is a continuous probability distribution. As the term itself suggests, in this probability distribution, the random variable is a continuous variable. And as we learned in a previous video, continuous variables can take on an infinite number of possible values within a particular interval contained in its support. We have systolic blood pressure as an example. Normal systolic blood pressure ranges from 90 millimeters mercury up to 120 millimeters mercury as per the November 2017 guidelines released by the American Heart Association. As we've also learned earlier, continuous variables allow us to have decimals or fractions. That being said, normal systolic blood pressure can take on an infinite number of possible values within the range of 90 to 120 millimeters mercury. The normal distribution is considered to be the most important and the most widely used probability distribution. In the medical sciences alone, a lot of continuous variables are assumed to follow the normal distribution, one of which is systolic blood pressure, which I just talked about. Now, Abraham de Moivre, an 18th century French statistician, was actually the first person to describe the normal distribution. Well, actually, it was more the normal approximation to the binomial distribution while he was studying coin flips, given that he was also a well-sought-after consultant of gamblers during his time. He noted that when the number of coin flips increased, the shape of the binomial distribution approached a very smooth bell-shaped curve. Now, this same distribution has been discovered independently by another French mathematician, Pierre-Simon Laplace, in 1778, when he derived an extremely important theorem called the central limit theorem, which I'll be discussing later in this video. Now, some years later, German mathematician by the name of Carl Friedrich Gauss, while working intensively on a theory on predicting the motion of the then newly discovered dwarf planet Ceres, used the normal curve to analyze his astronomical data. Now, his work later got published in 1809, and since then, the normal curve began to be referred to as the Gaussian distribution. Now, interestingly, the original published work of de Moivre was discovered in 1924 by English mathematician and biostatistician Karl Pearson, who by then already introduced the term normal distribution, something which we widely use to this day, just to avoid any dispute about authorship of this distribution. Now, despite this discovery, unfortunately, it was already too late. The eponymous term for the normal distribution, the Gaussian distribution, was the one that stuck. A word of caution, however. The term normal here does not at all mean a state of health or absence of disease or being free from any disorders. By saying normal in this sense, we are actually referring to the statistical characteristics of this particular distribution, which I will be discussing a few slides from now. Now let's first do a little review. In the binomial distribution video, we learned that the probability that the discrete random variable x, which is the number of successes in a series of Bernoulli trials, assumes a particular value can be computed using this formula. Now, if the discrete random variable is the number of times an event occurs given a particular time or space interval, and is said to follow the Poisson distribution, we make use of this formula in calculating probabilities instead. Now, in their respective videos, I've been referring to them as probability equations, but actually there's a proper term for that. It's called the probability mass function, often abbreviated as PMF. Now, this is the function that gives the probability that a discrete random variable is equal to some value. Now, a function in the mathematical sense refers to a relationship or expression involving one or more variables. Now, as you'll often see in textbooks, this term, which is read as the probability that random variable x assumes a particular value, is often replaced by this term, which is read as f of x. Now, in the case of the normal distribution, since the random variable of interest is a continuous variable, we refer to the function not as a probability mass function, but rather as a probability density function, or PDF. Now, this is defined as the function of a continuous random variable whose integral across an interval gives the probability that the value of the variable lies within that same interval. Now, the integral is represented by this symbol for those who've had calculus previously. Now, a good knowledge of calculus is definitely a useful skill to have when dealing with biostatistics, but for the purposes of this video, it's not an absolute requirement. Now, this is the probability density function of the normal distribution, which I'll be referring to as the normal distribution PDF all throughout this video. In the normal distribution PDF, x is our continuous random variable, which theoretically can take on any value between negative infinity and positive infinity. We also have two well-known mathematical constants, namely pi and Euler's number, the latter of which you've already encountered in the Poisson distribution video. The Greek letters mu and sigma are the parameters of the normal distribution, and they represent the mean and standard deviation of that particular normal distribution, respectively. Now, these are what's called the measures of central tendency and dispersion, which we'll be taking up in a subsequent video. But just to give you a quick definition for each, mean basically means average, and standard deviation is a value or calculation that basically indicates the extent of deviation of the different values in the distribution from the mean or average. Now, essentially, the only variable here is x, and all the others are constants. A particular normal distribution has its own mean and standard deviation, and these values, that is the mu and sigma, are therefore constants for that particular normal distribution. Now, this is the bell-shaped curve of the normal distribution. In this figure, the tails of the curve appear to touch the x-axis, but actually the tails are what's called asymptotic, which means that they approach but never touch the x-axis. They just go on or extend forever on either side of the curve, with the space between the tails and the x-axis becoming smaller and smaller, but the two will never meet or touch. Now, notice the symmetry of this curve. The vertical line that divides the curve into two mirror images intersects the x-axis where the mean value of the distribution is. So another important characteristic of the normal distribution is that it is symmetrical about the mean. Now, because of this symmetry, the mean of the distribution equals the median. The median is actually the value that lies at the midpoint of a frequency distribution of observed values. Now, this means that 50% of the observations fall below the median, and the other 50% of the observations lie above the median. Now, in a normal distribution, the mean is also equal to what's called the mode. The mode is the value that occurs most frequently in a given set of observations. Now, note that the highest point of the curve is where the mean is. Now, the y-axis here indicates the frequency in which a particular value occurs. So the highest point of the curve represents the value that is the most frequently observed. Now, this is also the same as the mean and the median. So overall, in a normal distribution, mean is equal to the median, which is also equal to the mode. Now, notice the other perpendicular lines besides the one that intersects the x-axis at the mean. At this point, let us momentarily ignore the actual values of the random variable x. With that, we standardize the mean by assigning to it the value of 0. I will be discussing what's called the standard normal distribution a little later. For the first adjacent pair of perpendicular lines, we assign the numbers -1 and +1 respectively, which means that each point on either side of the mean, which is 0, is one standard deviation away from that mean. Notice that the area enclosed by these two perpendicular lines, the x-axis below and part of the bell-shaped curve above, is about 68% of the total area under the curve. If we extend these perpendicular boundaries 2 standard deviations from the mean, the area now enclosed is 95% of the total area under the curve. Now, extending these perpendicular boundaries even further at 3 standard deviations away from the mean, the area now is 99.7% of the total area under the curve. Now, just as with any probability distribution, the total area under the curve is equal to the probability of 1. Recall from a couple of slides back that the mu and sigma, which are the mean and the standard deviation of a particular normal distribution respectively, are what's called the parameters of that distribution. Basically, we only need the mu and sigma to determine the shape of the curve as well as the position of the curve along the x-axis. The mu, or the mean, is the parameter that determines the position of the curve along the x-axis, in which the value of x increases as one moves towards the right along the x-axis. On the other hand, the sigma, or the standard deviation, is the parameter that determines the shape of the curve. Notice the shapes of the curve as the sigma increases. A smaller standard deviation would mean a narrower bell-shaped curve, while a larger standard deviation would mean a wider bell-shaped curve. As we will learn later in a subsequent video on measures of dispersion, experiments that yield smaller standard deviations are said to be more precise, while larger standard deviations result in less precise estimates of the mean. Now, as mentioned earlier, many continuous variables in medicine are assumed to follow the normal distribution. Now, this table here shows a few of those continuous variables. Now, let's say we have a group of, say, 200 patients. In this group, we have the following mean values and standard deviations for each of the continuous variables listed. As you can see, these variables have very different corresponding values, which will mean that their corresponding bell curves will have different positions along the x-axis. Notice that they have different units of measurement as well. Now, let's use systolic blood pressure as an example. Here we have again our normal distribution PDF. Let's consider the group of 200 patients to be our whole population, and with that we assign 119.7 millimeters mercury to our mu and 10.9 millimeters mercury to our sigma. Now, if we are to draw our bell-shaped curve, our mean, which is in the center, will have a value of 119.7 millimeters mercury. Now, just a few things about the continuous random variable x. Theoretically, x can take on any value between negative infinity and positive infinity. But of course, here obviously we can't have a systolic blood pressure of 0 and still be normal and alive. And having a negative blood pressure is just not possible. Now, if these 200 individuals happen to be disease-free, perhaps a credible systolic blood pressure range would be from 90 millimeters mercury to, let's just say, 125 millimeters mercury. So basically the take-home message here would be, for any continuous random variable to be considered, we have to at least know what the biologically plausible values are of it, and not just accept the measurements at face value. Now, going back to this exercise, what if we want to find the probability that an individual selected at random from this group of 200 patients will have a systolic blood pressure between 100 and 120 millimeters mercury? How do we go about solving it? Now, recall from the definition of a PDF, the integral across an interval gives the probability that the value of the variable lies within that interval. Now, our interval in this case is from 100 millimeters mercury up to 120 millimeters mercury. So, using the normal distribution PDF, we integrate these values using calculus to be able to get the desired probability. We have an issue here. Now, integrating this PDF is quite complex, especially for those with no background whatsoever in calculus, or even for those who've had calculus before but have now forgotten the concepts and techniques. Now, just for kicks, let's go ahead with solving this the hard way. So first, we bring the constants out across the integral sign, and afterwards, we try to simplify the exponent to this, and from there, perhaps substitute the value within the parenthesis with another variable, say u, then continue integrating, but this time with respect to u. So fast forward, this whole business results in creation of what's called the error function, or ERF, that you see here. Now, evaluating it using our boundaries, that is 100 and 120 millimeters mercury, we get the desired probability of 0.46605, which is the probability that a randomly selected patient from this group of 200 will have a systolic blood pressure of between 100 and 120 millimeters mercury. Now imagine doing this difficult and tedious task to all the other variables. We have to perform integration every time we come across a new set of parameters, which are our mu and sigma. Fortunately, we can convert the different normal distributions into what may be a one-size-fits-all kind of distribution called the standard normal distribution, which has a mean of 0 and a standard deviation of 1. Also, there are tables of normal curve areas as well as statistical software available which we can use at our disposal, thus circumventing the need to integrate. Now, just how is standardization of the normal distribution performed? We do that by basically creating a new variable, z, which is given by this formula. Z is equal to the quantity of the value of our random variable x minus the mu, or the standard mean, divided by the sigma, or standard deviation of distribution. The resultant value is what is termed as the z-score. Now, substituting the terms to the normal distribution PDF, The standard normal distribution PDF would then be like this. Now, let's compute for the corresponding z-scores for 100 and 120 millimeters mercury from earlier. With that, we get negative 1.81 and 0.03 respectively. Integration using this new standard normal distribution PDF with the computed z-scores as boundaries becomes slightly easier. Still difficult nonetheless. Our desired probability is now 0.4768. Now, since a new variable in the form of z was created, it is perhaps expected that the resultant probability is slightly different from the one that was computed earlier, but nonetheless, the two probabilities are quite close to each other. As I mentioned earlier, we can avoid integrating by using tables of normal curve areas, wherein we make use of the z-scores we computed. Now, before I show you how to compute for the desired probabilities using the tables, let me just mention a few things about them first. Now, these tables are also called the tables of standard normal probabilities because we'll be using the z-scores we computed to locate the probability values on the table. Now, there are actually two tables, one for negative z-scores and one for positive z-scores. Now, lastly, but nonetheless something quite important, the probabilities given the tables represent the area to the left of the z-score. Now, let's go back to the z-scores we calculated. I personally will always start with the z-score that's on the left with respect to each other along the x-axis. That would be z1, which is negative 1.81. Now, this z-score would have a smaller corresponding area to its left compared to the other z-score. Now, since our z1, negative 1.81, is negative, we make use of the table for negative z-scores. This table I got from the textbook of Daniel and Cross. Now recall that our first z-score is negative 1.81. We then trace where the row and column intersect. And there we have the probability or area to the left of that z-score, which is 0.0351. The other z-score we have is positive, so we use the table for positive z-scores. That z-score is 0.03. We do the same thing as previous, and the probability or area to the left of this z-score then would be 0.5120. Now that we've gotten those, let's go back to the original question. We are interested in the probability that a patient selected randomly from this group of 200 patients would have systolic blood pressures between 100 and 120 millimeters mercury. Now at this point, we've already established that we have to regard probability as the area bound by the perpendicular lines corresponding to the z-scores, the x-axis, and part of the bell curve above. Now as far as the original question is concerned, we are interested in this area here. Now how do we solve for that? Well, since the values we got from the tables are the areas to the left of each z-score, we simply subtract the smaller area from the larger area to get the desired area. Now that desired area or probability would then be 0.4769, very slightly different from the computed one because of rounding off. Now some of you may have encountered the term standard error and would wonder, how is that different from standard deviation? We will actually revisit that when I talk about inferential statistics in a subsequent video. Now remember how it is impossible to test or observe each and every patient in the world for a particular disease, for example. Therefore, the best we can do is to compute for a sample size that sufficiently powers our study, randomly select that number of patients from the population at large, analyze the data obtained from that sample, and then make inferences about the population based on the results from that sample. Now, if the standard deviation is a calculation that gives us an idea of the degree of deviation of measurements from the mean, the sample error, or more accurately, the sample error of the sample mean, on the other hand, is an estimate of how far the mean of a randomly drawn sample is likely to be from the mean of the population from which the sample was drawn. Of course, the true population mean is unknown, so the best we can do is to make sure the estimator that we're using produces an unbiased estimate of the population mean. Now, by the way, the population mean is designated as the Greek letter mu, while the sample mean is designated by x bar. Similarly, the population standard deviation is designated by the Greek letter sigma, while the sample standard deviation is designated by lowercase s. We will encounter this again under inferential statistics and hypothesis testing. Now, let me wrap up this video by discussing normal approximation to the binomial. For that, I have to go back to the example we had previously in the binomial distribution video. That example was about the use of low tidal volumes when ventilating intubated ARDS patients. Now, focusing on the low tidal volume group, we see that the probability of dying in that group is 0.31. Recall as well that the outcome variable is dichotomous, meaning the patient either survives or dies during the follow-up period and follows a binomial distribution. Now, recall that N is the number of patients who were randomly drawn from the population of ARDS patients ventilated with low tidal volumes. X, on the other hand, is the number of patients in that randomly drawn sample that experienced the event of interest, which is death. Now, recall that we previously tabulated all the resultant probabilities for all possible discrete values of X given an N of 5. It is important to note that the probabilities here in the last column are not cumulative probabilities. Now, recall as well that we graphed these probabilities in a vertical bar graph, and this was the kind of graph that we got. Note that x is equal to 1 has the highest corresponding probability at 0.35. Now, remember the shape and orientation of this graph because we will be comparing it to other vertical bar graphs that will follow. Still with the same p of 0.31, what if we now increased the n to 10 and did the same thing of tabulating the resultant probabilities for every possible value of x? Graphing the probabilities in another vertical bar graph, we get this. Again, take note of the shape and orientation of the graph. We see that this time x is equal to 3 has the highest resultant probability at roughly 0.27. Now let's repeat the whole process, this time with n equals 20. Graphing the probabilities in a vertical bar graph, we get this. At this point, you may be noticing how the shape and position of the graph is evolving. Now let's go even further and graph the probabilities when n is equal to 50. Notice how its resultant graph looks like compared to n equals 20 and n equals 5. See how the probability distribution has smoothened to assume a symmetrical bell-shaped curve. And with that, let me introduce a new term, the sampling distribution. Now, what is it and how does it relate to the probability distribution? Now, let's go back to our example, which is the low tidal volume study. We saw from the study that among intubated ARDS patients ventilated with low tidal volumes, 0.31 or 31% of them died. Now, if a random sample of, say, size 10 was drawn from this particular group, it is unlikely that exactly 30% of the patients in this particular sample will die. I mean, it could easily be lower or higher than 30%. Now, let's say this is the information we got from that particular one-time sample of 10 patients. It so happened that 4 of them had an outcome of death, which was assigned a notation of 1. So the proportion of deaths in this sample would then be 4 out of 10 or 0.4. Now, notice too that 0.4 is actually the average of all the ones and zeros in the outcome column. So in that way, we could actually regard a proportion as some sort of mean or average as well. Now, what if we repeatedly drew all possible samples of size 10 from the low tidal volume group? Each time we came up with a different average, meaning there's an average generated for every sample of 10 that was drawn. And for every value of the average we got, we tallied them to be able to get the frequency or probability of each average value. If we graphed these frequencies or probabilities against their respective averages, we come up with what's called the sampling distribution. Now, probably you'd start wondering, how does this tie up with the binomial and normal distributions? Allow me to explain by revisiting the characteristics of the binomial random variable x, which we already took up during the binomial distribution video. Recall that the mean is equal to n times p, and the variance is equal to n times p times the complement of p, or 1 minus p. Thirdly, this binomial random variable x is approximately normally distributed when the sample size, or n, is large. We actually have what's called the central limit theorem to thank for this. The central limit theorem actually forms the foundation for inferential statistics, and according to this theorem, the sampling distribution of the mean approaches a normal distribution when the sample size increases. Now, I haven't really encountered this figure yet in biostatistics references, but from what I was taught, there's this so-called magic number of 30 beyond which the graph of the sampling distribution already very much resembles the normal distribution. I guess I'll just leave it at that. Now, this one I sort of alluded to earlier when I mentioned about the proportion being the sum of all the ones and zeros, which was divided by the sample size of 10 from earlier, a value that is practically a mean or average. Now, references would say that the sampling distribution of proportions can be considered as a special case of the sampling distribution of the means. Now, for purposes of this video, I won't be going into the details of the central limit theorem, though I might eventually put out some videos in the future that would expound more on the theory behind it. Now, when is this approximation appropriate? The sampling distribution of the proportion, or p, is said to be approximately normally distributed if the sample size is sufficiently large. We've already heard about that from the central limit theorem. The general rule of thumb for us to say that a sample is sufficiently large is that the product of n times p is at least 5, and n times the quantity of 1 minus p is also at least 5. Now, mind you, some references might recommend a number a bit larger than 5. Now, there's a caveat to this though. As one can figure out already from the general rule of thumb, the sample size need not be that large if p is rather near to 0.5. But how about with the extremes, that is for small and large values of p? Now let's take p of 0.01 for example. In order to satisfy the rule of thumb that n times p is at least 5, the sample size has to be at least 500. A similar thing can also be said about a p that's equal to, say, 0.099 or rather 0.99. In order to satisfy the rule of thumb, the sample size has also to be at least 500. Now, be aware that these rules of thumb are actually guided by statistical practice, so as long as these conditions are met, the normal approximation to the binomial distribution can be used appropriately.